The last form of cis-trans stereoisomers are looking at our alkenes. The carbon double bond in an alkene is what creates that locked plane or is fixed. So we need to look at the groups on either side of that double bond to determine if the structure has cis or trans designations. As we approach an alkene, we want to be able to identify where the fixed carbons are at and if the groups on either side of the double bond are the same or different. So we're going to draw that vertical line separating the two carbons participating in that double bond. We want the groups on either side of that line to be different. So here we have a methyl and a hydrogen, different, and we've got a methyl and a hydrogen. Those are each different from each other, which means that we can move forward with having cis or trans stereoisomerism. Lay that line horizontal, and then we want to find that longest parent chain that has that double bond to see where those groups are at. So if I follow that chain, I can see where my highlighted tracks are at, and that those two methyl groups are both above that double bond. Because they're both above that double bond, that is going to give us cis 2-butene. Now, we're not always going to break out the structure with those groups around the double bond as shown in this first one. So I have two other images in which you need to be able to recognize. The second one does not include the bonds between the hydrogens, but you can still kind of see that U shape. But more importantly, it is going to be the skeletal structure. You will see the skeletal structures, especially when we get to lipids, when we have really large hydrocarbon chains, that cis and trans dictates the properties of those fatty acids. So in a cis skeletal structure, it creates that bucket, essentially. We call this a kinked chain or a bent chain. These are easier to react with because the double bond is exposed to an attacking group. So they tend to be more reactive or easier to break down. Let's follow the same pattern. Looking at our vertical line first, are my groups different on either side of that double bond? They are. So we could have that cis-trans conformation. Now we're going to go that horizontal so we can track the groups. So I'm going to follow that longest parent chain, and I see that my color or the track that I'm using to for my parent chain is going across that double bond. Because it's going across that double bond, that means it is trans. Therefore, this is trans 2-butene. Again, we don't readily pop those hydrogens out from that double bond. So looking at the structure, because our hydrocarbons kind of naturally go into this zigzag or peak and valley structure because that maximizes the distance of electrons from each other, creating a more stable cloud. We can see that in that trans, it maintains that zigzag, whereas the cis did not. And in that skeletal structure, you can continue to see that zigzag. It maintains the hydrocarbon chain geometry. Trans are usually more stable and less reactive because those groups that are going to attack that double bond are a lot more protected because of the way in which that double bond is placed in relation to those other groups. And we're going to talk about the importance of that positioning when we get to lipids. The last one, I suggest pause. See if you can do this yourself, and then I will go through and do it with you. Starting with my vertical line, looking at my groups, I have a methyl and I've got an ethyl. Those are different. I've got an ethyl and a hydrogen. Those are different. So I have a cis-trans configuration. Go horizontal, find the longest parent chain. Those are where the electrons are going to be so that we can identify cis or trans. So we have this double bond and we want to maintain the longest parent chain. So it's going to go to the ethyl groups on either side. Based off of this, we can see that those groups are opposite of each other. So we know that this is going to have a trans configuration. Now we need to name it, keeping in mind we do have this additional methyl group. We want that carbon on the double bond to have the lowest locant possible, and no matter the way in which we number that chain, it's going to be 3. So then we need to number the methyl to have the lowest locant possible, and we also want that to be 3. So it's going to be either 3 or 4. 3 gives us that lowest. Therefore, this name is, I'm going to need more room, trans 3-methyl 3-hexene. that was the longest, right? And we can track, again, showing the different ways in which we can draw them, putting that double bond in that trans position so that the zigzag still maintains, showing that it is trans as well.